Hello everyone, my name is Milda Rusydiana and welcome to this video where we will explore one of the most fascinating concepts in modern physics, time dilation. Time is a fundamental quantity for illustrating our world. The elapsing of time allows us to measure the movement of objects for a long time. People think time is absolute, with a single clock for the whole world, which ticks at the same rate for everyone, everywhere. However, the theory of special relativity fundamentally changed our intuitive perception. Time is no longer absolute, it is relative. Each object has its own clock, which measures the time elapsing from its own perspective. In 1941, an experiment was carried out by measuring the lifetime of muons at different speeds. The muon lifetime at rest is about 2 microseconds, while a cosmic ray produced fast-moving muon can live 5 times longer. How do we explain this phenomenon? How can it be the same kind of particles have the same lifetime when they travel at different speeds? To answer this question, let's imagine there is a train moving forward at a constant speed. Meanwhile, a dog is standing stationarily watching the train. Imagine a passenger on the train throws a ball toward the front of the train. For him, the ball is moving forward with a certain speed. However, from the perspective of the dog, the ball seems to be moving faster because its speed combines with the speed of the train. The strange thing is if we do the same experiment with a torchlight, we will see that the speed of light remains the same regardless of whether we look from a stationary or moving perspective. The speed of light is invariant. It is a universal constant that never changes. To understand how time elapses for fast-moving objects, we can design a clock beam of light bounces between 2 mirrors. Whenever the light hits the bottom mirror, the clock advances. We give each object its own clock. All of these clocks tick at the same speed when they are stationary. But what happens when the train starts to move? The light beam in the moving clock travels a diagonal path. According to the Pythagorean theorem, the diagonal path is longer than the vertical path. Given the speed of light is constant, the light beam in the moving clock will take longer to strike the bottom mirror. That is to say, from the dog's perspective, it will observe the clock of the passenger is running slower. This phenomenon is known as time dilation. In reality, the speed of time elapsing has never changed. It is simply a matter of perspective caused by the relative speed of different moving objects. From the passenger's point of view, he is stationary. It is the dog that is moving in the opposite direction. Thus, it is the dog's clock moving in slow motion. Let's go back to the experiment that measures the lifetime of muons at different speeds. Stationary muons generated in the laboratory have an extremely short lifespan. They disappear after only a few microseconds. However, the cosmic ray produced muons have a much longer lifetime. This is because their falling towards the ground can reach an extremely high speed, which is super close to the speed of light. The obvious time dilation effect dramatically slows down the evolving of those fast-moving muons, so that they can have enough time to travel through the atmosphere and reach the surface of the Earth. So, let's get started. Question 1. Explain that a rocket ship travels at a constant speed of 0.8 times the speed of light relative to the Earth. A clock on the rocket ship records a journey time of 4.8 hours. Part A asks what the flight time will be when measured by a clock on Earth. What is actually being asked in the Part A is the relativistic time, usually written NT prime, because the question states that a clock on board the rocket ship, which is in the same frame of reference as the moving object, records a time of 4.8 hours. This means that the 4.8 hours is the proper time. To solve this, we first write down what is known from the question. We are trying to find the relativistic time, T prime. The proper time, T, is equal to 4.8 hours, and the velocity of the rocket, V, is equal to 0.8 times the speed of light. The velocity is left in the form 0.8c because when it is substituted in the time dilation equation, the speed of light term will cancel out. Using the time dilation equation, the relativistic time is equal to the proper time divided by the square root of 1 minus the square of the velocity divided by the speed of light. Substituting the given values into the equation result in 4.8 hours divided by the square root of 1 minus 0.x squared. Because the speed of light apart in both the numerator and denominator, it cancels out. Evaluating these expressions using a calculator gives a relativistic time of 8 hours. Thank you so much for watching. I'm Milda Rusydiana, and I'll see you in the next exploration.